Morning. So while my kettle is boiling, while I'm gonna have a cup of tea in a minute, I thought I'd just have a little quick video about reading current time curve. What's a current time curve, Richard? I hear you say. Well, the current time curve looks like this. It's found in Appendix 3 of BS 7671, and it's a graph, a chart, if you like, of all the different or popular types of overcurrent protective device. And from this graph, we can work out what the disconnection time or operating time of that device is based on the value of fault current. So you see we've got two scales. We have time, this is the disconnection or operating time, and we have this scale horizontally here, which is your value of fault current. All right. We've also got, as you noticed, so this is the B-type breakers, BSEN 61898 or RTBOs to BSEN 61009, normal kind of standard domestic devices. And you've got a line curve to represent each value. So we get 6 amp breakers, we get 10 amp breakers, 16 amp breakers, 20 amp breakers, right up to, if you want, 125 amp circuit breakers. You have a curve for each of those ratings. Got to be careful with the scale of these. This is what they call a logarithmic scale. Okay, and you can see that the scale goes up in factor of 10 every time. It starts at 0.01, 0.1, 1, 10, 100, 1,000, 10,000. Normally we'd expect that to be, sort of 0, 10, 20, 30, 40, 50, but it doesn't. It goes up in factor of 10. It's logarithmic, which is fine. We've just got to be a bit careful about the way that you read off it. And I'll show you an example why. This is the line that represents 1 second. So this one would be 2, 3, 4, 5, 6, 7, 8, 9, up 10. That doesn't mean that this line here is 11. This line here is actually 20, 30, 40, 50, 60, 70, 80, 90, 100. And it doesn't mean that this line is 101. This is actually 200, 340. So you've got to be careful about how you read the scale, and it's the same for time. Here that represents 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6, 7, 8, 9, 10. Doesn't mean that this line is 11. This line is 20, 30, 40, 50, 60, 70, 80, 90, 100. So you've got to be really careful about how you read the scale. Now, for some reason, BS 7671 decided to put this text box here, which completely obscures the bottom part of the graph. Thanks for that. Thanks very much. So if you're trying to read something like maybe, say, 400 amps, you can't see where the bottom of the line is. You're going to have to kind of read it across up here. So that's about the scale. Current across here. Make sure you choose the right table for the device that you've got. They also do tables for C-type breakers and D-type breakers, as well as semi-enclosed fuses to BS3036. They do fuses to BS88-2, which is your HRC, HBC fuse, BS88-3, which is, or what used to be BS1361, which is your normal kind of cartridge fuse, general purpose cartridge fuse. So you get a graph for each of those, so you have to choose the right one. So what's also worth mentioning that you can see that part of the graph here is curved, and then it goes straight, curved line, straight line. And what that's representative of, within the device, within a circuit breaker, I'll just zoom in a little bit. Within a circuit breaker, there's two devices in one essentially. You have the bimetal strip that deals with the smaller fault currents, say from an overload, a small sustained overload. Then you've got the magnetic part that deals with a heavier fault current, say maybe a short circuit. And think about the curve line, okay? You can see how as we increase in current, the time decreases. And the reason for that is because as the fault current increases, it will heat up the bimetal part inside the circuit breaker, okay? And as the current increases, the more it will warm up. And the quicker it warms up, the quicker it disconnects. So essentially, the bigger the value of fault current, then the quicker that device will disconnect. So the curved part here is dealt with by the thermal part, the bimetallic strip within the device. And then the straight line represents the magnetic part inside the circuit breaker that deals with short circuit. And what it's basically saying is that for this 6 amp circuit breaker, okay, once it reaches 10, 20, 30 amps, that is the point at where the magnetic part of the circuit breaker takes over and comes into play. And at 30 amps, it will just operate. It doesn't matter how much more current you stick into it, if it's 50 amps, 100 amps, it'll just disconnect, bang, from that point there. So the curved part represents the thermal, the bottom part represents the magnetic operation of the circuit breaker. Let's then clear that off, and we'll have a look at maybe looking at an example of how to read a current time curve. And you may be wanting to know in this example, how quickly will a 20 amp MCB B-type, because it's the same graph, how quickly will that operate at a fault current of 90 amps? The way you go about this is that you read across the scale. Let's have a look at the current first. We're having a fault current of 90 amps flowing, so that's 10, 20, 30, 40. Thank you, BS7671, for sticking that stupid box in the way. That's 50, 60, 70, 80, 90. So 90 amps is represented by that thin line there. What you then need to do is read up on that thin line until it reaches the curve for the device that you have. So this is the curve for the 20 amp circuit breaker. All right, so you read up from there. May help you to use a ruler at this point, so you can get a ruler and just see the point where your 90 amps of full current reaches that curve. What you then do with maybe another ruler is you then read across to see the time scale, and that ended up about there. Okay, it's a bit of a rough size, you know, you're going to get it spot on accurate. So bearing in mind that that line there is 10, this line here is 20 seconds, I'd estimate that to be about, what, about 17 seconds maybe. Which is a bit scary, isn't it? You've got a fault on a circuit. What would a 20 amp MCB do? So maybe it might be supplying a radial socket supplying socket outlet. The radial socket supplying sockets, but it's 2.5, 20 amp breaker. That's an A3 radial. As many sockets as you like within 50 square meters. But if it has a fault current of 90 amps, that's going to take about 17 seconds for that device to operate. That's pretty scary. So your bit of 2.5 will carry 90 amps for about 17 seconds. Pretty scary. But that is the nature of the world. So what did we do then? Just to jog back, we found 90 amps on the scale, which is just about there on this line. We read up until it crossed the device line that we're looking at. There's the line that represents 20 amps. We found where 90 amps dissects it, and at that point then we read across to read the time. Let's just do one more example. This time we've got a 6 amp MCB with a fault current of 20 amps. This will be a bit easier because our text box isn't obscuring our current. This line represents 10. This next line represents 20 amps. Let's now go up and see where that dissects the 6 amp line, which is just about that point there. And then we can get another ruler and just read across. Now that's quite nice, because it fits quite nicely, doesn't it, on that line there, whatever that is. So let's read that across. So if this line is 10, that one will be 20, this one is 30. So at 20 amps of fault current on a 6 amp circuit breaker, that would disconnect in about 30 seconds. Which is again a bit scary. This 6 amp circuit breaker might just be doing a lighting circuit, 1 mil to an earth, that can suddenly have to carry 20 amps, and it'll be like that for 30 seconds. So that's how we measure disconnection time given the value of fault current. So you measure across to find your current value. You then go up, you follow the line up to where it meets the line, the curve that represents your device. Then you read across to get the time. And that's it, but I thought what I'll just show you, I'll show you the whole page. This is the whole page that you'll see in BS7671. And this is the page then for type B circuit breakers. Now what you may notice is we've got a table here, and you'll find one of those on each of the curves. And what this tells you, this table here, and then let's have a look at the next slide. I'll zoom it in a bit. It tells us at what current we're going to reach what they call instantaneous disconnection, or 0.1 seconds, or basically it's when the magnetic part comes into play, the full current at which the magnetic part kicks in. And you can see then for a 6 amp circuit breaker, a full current of 30 amps will cause that device to disconnect in 0.1 of a second, which is there. And for a 16 amp circuit breaker, you can see then that it takes 80 amps for that magnetic part to come in and give you that instantaneous disconnection. So any fault greater than 80 amps on a 16 amp breaker will just cause it to disconnect instantaneously, and we'll take that value to be 0.1 seconds. If it ever came up, you may notice that for a C-type circuit breaker, the instantaneous disconnection value is 5 times the rating. Right, so I take 6 multiplied by 5, that gives me 30 amps. And if I 10 multiplied by 5 is 50, 20 multiplied by 5 is 100. So basically for B-type devices, you get instantaneous disconnection at 5 times its rating. It's not like that for all devices. For example, C-type, it's 10 times its rating. And I'm going to show you the table, you can just take my word for it. But anyway, I hope that's shown you how we can read current time curves. And don't forget, the curvy part is for the thermal, the straight line part is where the magnetic part of it happens. Be careful when reading the scale, and do a few examples with yourself. Get yourself a Regs book, open up Appendix 3 and just look at the curves and have a little practice. But until then, I'm going to leave you to it. Bye for now.